Thank you, Susan. Thank you for the introduction. It's always a pleasure to be with you, even if it's just via Zoom. I would like, before beginning, I would like to be sure that I am acknowledging my my collaborator here. I think that I've trouble with Jin Shengyang. So Jin Shengyang, which is a former student of mine. This is the equation, and that's what I want to talk about. I will keep trying, but okay, trying to not be worried about that. Okay. So this is the equation. The equation, you know, it is an incompressible Navier-Stokes equation in a periodic terminal. This omega here that we'll consider physical boundaries, so up and down, so z equal to 0, z equal 1. On the other variable is just periodic, right? So that's why I will have, or you know what, I will use it that way. You can see it, right, on my things. So, well, it's not as good, but it will be okay. So here, so you have the equation, it's Navier-Stokes. What I would want to consider was happening for a very small viscosity, inviscid limit, so that what you have a nu for the viscosity here, right? And it's basically the idea of what I want to investigate. I mean, it's a very known problem about the effect of boundary and inviscid viscosity. Divergence free, u equal to 0, so it matters only at z equal 1 and z equal to 0. And basically, what I want to see what's happening when you are close to shear flow. A given shear flow, AE1, so close, not exact, of course, but close to a shear flow for the initial value. And I put A here, so E1, so this means the shear flow with respect to the physical boundaries. And I put A here in order to measure the strength of this shear flow. Especially, it will be interesting to see what's happening when the strength is not that small. I mean, we will see this in details. Okay, so it is, and you have actually a specialist in the room here, in the Zoom room, about this kind of problem, right? I mean, a major problem to know whether this limit nu converge to the shear flow for time positive when the viscosity converges to 0. So here is double limit, right? This will be a limit viscosity converges to 0 and initial value converging to the shear flow. So if, of course, if you consider exactly the shear flow AE1 as an initial value, then the solution of the Navier-Stokes corresponds exactly in this simple case to the Prandtl layer, right? And I won't be able to make a picture here, but I was supposed to. So you have, of course, only the effect of the heat equation here. You don't see the non-linear effect because it's a flat boundary. It's very simple. And when you consider exactly this solution, well, the typical scale here is square root of nu, right? Because it's linked to the heat equation. But if you consider perturbation on the initial values on top of just taking the viscosity initial value, then up to now, I mean, this is basically in terms of looking at the inviscid limit and hoping that you get the shear flow at the limit, where there's only conditional results, and especially there's Cato criterion, very famous from 1984, which said that actually, well, all the information in order to have this limit, right? So it's just under the limit that when you converge to 0, your initial value converges to the shear flow, right? And you would like to know if you converge to the shear flow, you have that under the condition that there is no dissipation very close to the boundary. And already you can see there is something really non-trivial which is happening. And again, I'm not talking for the specialist in the room who knows here far more than me, but it's always interesting to remember that things are another scale, right? Because here is for z close to r nu. So this means it's not the scale of the Prandtl layer, right? I mean, this Prandtl layer is square root of nu, so it's small, but it's not that small. And here we are looking really in a very, very small layer here, which is a nu. And I'm really feel bad about this things. No, okay. So this is where things, and if you can control the dissipation of energy, kinetic energy here, right? I mean, really at the level of nu, and then show that this quantity converges to zero, very close to the boundary, then you will converge to what you're looking for. So, I mean, certainly everybody knows very well this picture. It's a very famous picture from Wikipedia, right? I mean, this is an airfoil. And basically, if you're looking at what's happening when you are close, when you have this Prandtl layer, this is what things happening below, right? These things happening here, and this is what you expect. I mean, what you hope for when you are in the plane, right? Because this makes the flow very stable, right? And you can see that actually at the limit, right? I mean, because the viscosity anyway is very small, it's for high Reynolds, especially here the Reynolds number is very high. Well, you have here a flow which is basically follows the boundary, right? But what we want to talk today is really about what things bad which can happen. Can, because we don't know, right? But so it's above, right? And in some way it's expecting in physics, but it's hard to pinpoint where in terms of mathematics, but that things can happen, bad things can happen, right? Because and it's linked to turbulence, right? And of course, so this is linked to what is called layer separation, which is basically on this picture pretty clear what's happening here, right? Is you have your layer here, things are nice far away, but close to your boundary, you have a big swirl here, and your flow is pretty far from what you expect. So I should say that the situation is not exactly as I showed here. It would be looking at the bottom, right, on the box, but of course the angle here is important, so I don't claim that I see exactly this, but this is the kind of problem that I want to investigate here. And even in terms of mass, actually, there is some prediction that things may be bad happening at the limits. If you do formally the limit, and here is completely formal, nu equal to zero, well, obviously what you obtain is the Euler system, right? And so you have nu equal to zero, so no viscosity anymore. You have the equation, divergence equal to zero. And of course, well, it's very well known that the u equal to zero, the non-slip condition, is replaced at the limit, well, at least that's what is expected formally, by the impermeability condition, the fact that nothing goes in, nothing goes out, right? I mean, u equal to zero is overdetermined. You wouldn't be able to find a solution like this. And of course, well, if you converge, well, you should expect E1, I mean, to keep exactly the shear flow, because that's what you were trying to get at the limit. But even in this context, if you consider just this problem, then there is a method of convex integration which shows that those solutions, the solution AE1, the shear flow, even for the shear flow as initial value, this solution is not unique. And so the proof was done in a very nice little paper by Shekilidi in the context, not in the context of boundary, in the context of shear flow inside the domain, but actually it can be reproduced exactly in this context with the boundary. And it's really rely on this computation, right? We just redo it. There's a nice trick just because we're interested in the case with boundary. And what they showed is that actually you can have layer separation, right? I mean, in this context, right? So solution which are energy decreasing, which are solution to the system, and on top of it, you can measure, and there's a little computation that we've done because we thought it was interesting. You can measure the energy of this layer separation by measuring the energy of the velocities of the solution, right, that you get, minus the shear flow. And what they show is that this energy on the specific examples that they compute, right, because they construct specific example, on those specific example, they can get a growth, which is exactly like times a cube, times a constant, and they can do it for any constant between 0 and 2. So that's their result, right? I mean, also that we packaged here. So in terms now of trying to go to Navier-Stokes, well, this is a general idea to say that, well, when you have those weird things happening for systems which are known to be a bit tricky, well, we can say, okay, if we really want to know if this happened physically, it makes sense to try to say, to see if we can get them as a limit of Navier-Stokes. Right. And there I will say, you have to be careful what kind of Navier-Stokes. I would say limit of nice Navier-Stokes, right? So it means, not weird things. At the Navier-Stokes level, it is better that you can. Initial value smooth. If you're 2D, smooth. If you're 3D, at least having the energy inequality, right? I mean, all the nice stuff. Can you get something, some information for what you can get nu equal to 0 and say something about what we can get. So here again, as I said, we are betting on the worst scenario. So on really the turbulence here. So what we want to show is, can we show that you cannot get worse than that, right? So the idea would be to say that, well, we don't know if there's separation because, again, this is an open problem, right? So when you take the limit, maybe you just have AE1, but let's try to prove that at least you cannot get worse that those solutions constructing by Székely at the level of Euler. And why not control to have actually a control even at the Navier-Stokes level? And that's basically what we get, and this is the main result. So it works for any dimension, I mean D2 or 3, and so you get the situation that I mean the picture before, right? So it's this box, this tunnel, right? And you consider a Navier-Stokes there. You pass into the limit. You can say, well, passing the limit in what? Well, it will be weak limit because anyway, those U are energy bounded, right? So you can always opt to a subsequent pass to the limit. I don't even know if you're 3D, if you're solution of Euler. I don't care. I just consider any of those weak limit that you get when the initial value converges to any one, just in L2, right? So no more. But the U nu 0 can be smooth, right? Any Lorraine up, you pass into the limit to the initial value. And what I can say is that for almost every time t, the separation of layer, if there is one, won't be worse that was predicted, I mean, was seen by those model on Euler by Székely. Right. I mean, except that this constant, I can say it's 2, but there is a universal constant, right? There is a universal constant, and you won't have a growth more than that. So basically, this corresponds to the layer separation predicted by the complex integration. Again, I don't show that you get it. I say that you cannot get worse. That's the result, right? So I think this is actually a line of work that I've been to have several works, but more in the compressible side, right? So it's basically the first kind of result of this kind that we have in compressible fluid. And it comes into a general kind of question, which is about predictability, right? I mean, it is a big problem, I think, if you work in fluid mechanics, especially fluid mechanics, which involve singularity, things shocks for compressible mechanics, right? To have all those non-uniqueness results. I mean, there's two possibilities. Either you say, well, those solutions are not interesting, but more and more we think they are, right? Because they are model of turbulence. And if they are, well, if you have non-uniqueness, how can you say that how can you use those models and the claims that you predict, for instance, the weather or whatever, right? So in some way, here is the first result that goes in the direction that we were looking for, right? Because if you look here in this situation here, the shear flow. So here it would be basically to say that, we want to say that the shear flow should be meaningful, right? Even if it's not unique. But if you look at this shear flow, and especially for small a, right, and this is small shear, then the energy of this shear flow, because the box is fixed, is a fixed box, is of order s squared. Like say, if the box is measure 1, is exactly s squared. Right? And what we prove is that in the inviscid asymptotic, nu converges to 0 was a double limit, right? And I think that double limit is important here because it means that you can expect some small perturbation in the initial value, but which at the limit disappear, right? In the double limit, initial value converge to your shear and inviscid limit, then the energy of the error, if you want, or the separation of the layer is of order a cube. Right? So it will be, if you have a small shear, a small pattern, if you want, a pattern that you're looking at, then you can predict this pattern, and you can say that actually you can give the time of prediction. You can say, well, this pattern will be visible, right, for a time which is like 1 over a. Right? And I think it's important. It's something that I would love to have for all the things, especially for shear flow in size domain. If you think about meteorology, right? Meteorology, and usually is you have the thing that you're looking at is small perturbation compared to the size of your atmosphere, right? And so what I would like to claim, I mean, this is the first, or to what I expect, right, would be to be able to show that some patterns like this, maybe not unique, but in some way, whatever the solution that you have, right, you can still predict that you will be close to this pattern, and you can predict the time with respect to the size. A typical example that I love is, and I mean, actually, I'm kind of, I mean, this is really what brought me into this point of view is tidal bore, right? So I don't know if you've seen tidal bore. Tidal bore is this kind of waves that happen in a river when there is a tide, when the ocean get up, and you have a wave which comes into the river. And well, this can be really modeled very nicely by a shock for the shallow water equation. So it's compressible here, right? But a tide. But this is exactly the solution for which we have non-uniqueness with the solution of Shikeli. We know that those solutions are not unique. And still, you can see in the Amazon, you can see them hundreds of kilometers far away from the ocean, right? So they are stable. But how you can say something is stable if it's not unique, right? But again, it's small pattern because the wave is very small compared to the size of the river, and you can see this is not unique because I've seen some in the Seine, right? So the river of Paris, you have to be pretty close. Maybe it was 10 kilometers from the ocean, and it was I was a kid. My father showed me it was maybe this side, and you can see. I mean, it's not a wave. I mean, it's a wave like a wave you can see, right? So it's not that you are very close up to the third derivative to your wave. It's not that, right? You have all those perturbations. They are here, right? So if you have non-uniqueness, you have to find another way to explain why you can see them so far. One, they are non-unique and stable. And what I explain is something like this. I cannot show it for the shallow water equation. The reason is because here the fact that it's on the boundary helps a lot, right? So, but this is the very first result, and it's for incompressible flow, right? Even if we work first for compressible, when we can have this kind of pattern. But I think it's important and it's interesting. Okay. Okay, so in terms of this, I'm sorry that there's a lot of work which has been done before, right? And actually, I feel bad because there is obviously in the audience people who know far better than me, right, about those line of work. But I would say there is basically two families of work, right? I mean, the family of Prandtl layer, and still a lot of interesting work and really not easy, right? Stuff there, but it's basically to understand in terms of my picture there, what's happening here, right? What's happening when things are fine. And surprisingly, what's happening when it's fine, it's not fine. I mean, it's really complicated, right? Already, right? And then there is things trying to rule out this kind of scenario, at least in the limit that we consider here. And basically, most of them goes around the Cato criterion. There is a lot of very nice and important improvement of it, right? I mean, working with vorticity, the work of Kelly, very interesting. There is some result if you add some symmetry that then you can show that, especially around Matsukato, Maekawa, or a regularity, right? I mean, for Maekawa, if the vorticity is far away from the boundary. But all of them, basically, there is I mean, you have an extra conditional result, and that's how I'm trying to claim that we have the first non-conditional result in the turbulent regime, right? But again, maybe a result which is not interesting, because if you converge to actually to A1 always, then it's not interesting. But at least it's unconditional, right? And of course, I'm talking about the limit of Navier-Stokes. So we know already that when you take limit on Navier-Stokes, you can get bad things. So this, I wanted here to cite the very nice result of Bigmaster and Bicol, limit of Navier-Stokes conversion to Euler, basically showing that you have all those bad behavior already as a Navier-Stokes. There's two reasons where things does not apply directly in our condition here. First, the result cannot handle, I think, for now, bounded domain, right? This is one problem. And the Navier-Stokes solution that they have are not suitable. They are not nice, right? And I claim that what we have is whatever the regularities, the things that you have at the level of Navier-Stokes, right? But it would be super important to have the other side, right? And I would love to have this kind of result to see that actually you can get, right? You can separate. That would be, of course, I mean, a result of another magnitude of interest, right? To show actually that you can get that. But I think that we're very far to have such a result. For me, I mean, even people working on this line of research. Okay, so what is the main idea of our result, how we get there? Well, actually reading stuff written by other people, I was really struck at the fact by looking at the paper of, I mean, it's a review, right, of Maekawa and Matsukato. And actually, I recited it because I said after the fact, it's not completely true, because actually, I was in Cannes, France, in AIM, so close to your place, and I was listening to Anna talking a lot, and that was part of where ideas came. And then I just read what she wrote and say, well, I understood better, right? But so let me just read there. So what's were written in that paper. Mathematically, the main difficulty in the case of the non-slip boundary condition is a lack of a priori estimates on strong enough norms to pass to the limit, which in turn is due to the lack of useful boundary condition for vorticity or pressure. Right? So basically saying that, well, this limit of no slip, which is exactly what we're considering, is hard because we don't have much information of pressure and vorticity on boundary at the level of Navier-Stokes, right? Even if you look at the limit. And that's basically what we were looking for, what we did. What we obtained is boundary vorticity control on the on-scale Navier-Stokes. So if you take nu = 1, right? So really at the Navier-Stokes level, we were looking for a regularization effect on the vorticity at the boundary, which gives extra condition effect that we wanted to be scalable through the inviscid limit nu = 0. So that's really this. It's obtaining regularity, a new regularity, I mean, regularization effect. You will see, I mean, it's a pretty low regularization effect, but still at the boundary of the vorticity, but one which can be scaled through, not only through the the scaling of Navier-Stokes, but also through the inviscid. So again, most of people here know about this, but let me remind you and why the vorticity is important for this kind of problem. So this is very simple here, is if you want to look at the evolution of the separation, energy of separation, layer separation here, right? Well, what you compute is u nu minus a1 squared. Well, it's a squared. So this is u nu squared, a1 squared was a constant, so I don't have it, and the product 2 u nu a1. And that's why here it's a tautology, right? It's just evolution of energy minus 2e1 derivative of u1 dx dz. I mean, it's what you find in the coefficient Cato, right? I mean, there's nothing here. Well, okay. Well, if you have a Lorentz solution, well, this is actually smaller equal, right? To minus nu gradient u squared, fine. But now if you take this evolution, right, it can be seen that actually at the level of Euler, you don't get anything, right? It's really the vorticity which come into play. And why? Well, I would have written here, but it's because dt of u1 is a u gradient u1, right? But it's just u1, right? And there is the pressure, but the pressure is d1p. It's a derivative of pressure here. But when you integrate, because there is no derivative of p along the real boundary, right? But it's along the thing. So the d1p disappear, right? And same thing for the u gradient, the u du1, because you have only, well, there is a dz, but it will give you the u at the boundary, which is equal to 0. So the term that come is really the term of the Navier-Stokes, is the new Laplacian, right? And if you do the new Laplacian, same thing when you integrate the dx1, dx2 disappear. If you just integrate new dzz of u1, you integrate, well, it gives you on the boundary new dz u1, right? And these things, and because the other part of the vorticity would be d1 of u3, but again, integrate d1, because d1, this is a torus, right, disappear. So you can really rewrite it as a vorticity, right? It's really the integral on the boundary and the vorticity. And it's very well known, is because you have some build-up of vorticity at the boundary, which then dissipate into the domain, right? And it's all about what's happening here. So basically what we want is to control these things, is what we do. And how we do this? Well, we do it by controlling the boundary vorticity, but at the level of Navier-Stokes. It's really a regularization effect. So we go back to Navier-Stokes, nu equal 1. And of course, we will do it with by rescaling. So we are very careful that our estimate here, which depends on the constant, this constant does not depend on anything, not on the side of the domain, because when we will zoom, the domain will be big, not on the side of the initial energy, because when you will zoom, the energy will be big. So it depends on nothing, right? It's a universal constant. That's very important. Okay. And basically we say, so you take a domain, a channel, but which can be very, very big or very, very small or whatever, and you consider the boundary, because the boundary result, so you have d omega time, so it's time boundary of your domain. And what we say is that whatever the Lorentz solution that you take here, u, well, there is a decomposition of this boundary, right? Which depends on you, but okay, and it's a parabolic dyadic decomposition, and such that why we need to do this, well, I will explain later, but such that when you take this mean value, so you replace the omega by the mean value of each of those domains, right? And when you do this, this regularized vorticity, if you want, have almost L3/2, you have almost L3/2 control of it on the boundary, depending only on the dissipation. Right? So these things means what? It means, well, this is after taking some mean, right? This is, well, for value which are big enough, but the small we don't care. There is a 1/t, it makes sense, it's a regularization effect. At t equal to 0, you have nothing, then you get something more and more and more. So that's why it's only for the omega big enough, okay? And here it would be L3/2, but it's weak, right? And this is a feature of all those results kind of that we have. So this is what you would get if it was using the what's the name? The estimate, the Chebyshev estimate, right? So this means the measure of the function bigger, etc., etc. And it's very important too, because we want to rescale it, is this norm at the power 3 over 2 controlled by gradient 2 squared, right? It's not only the fact that you control the L3 over 2, which is important, which is already something that was not known in 3D. In 2D, actually, it was, I guess it can be done by other methods, but in 3D. But the important thing, which was known before, is that you can control exactly that way, the L norm 3 over 2 by gradient 2 net. Right? And why you want this? Because you want to be able to rescale it, right? To rescale it through the other side. Okay, so that's super bad. Oh, it works. Okay, very good. I don't know why, but I will jump on it. Okay, so how we do, not why yet, but how we do those smoothing effects. Well, the first thing, right, is that you can see here, if you do a first a partition, right? And you can see this partition very thin, close to t equal to 0, less after. It is kind of natural again, it's a regularization, but it's not enough. And we may need, and usually we have, to partition more. And this is dyadic. And basically, we cut it, and I will explain more in detail later, not very late. And basically, we cut it, and we check, and we say, well, is it fine? Well, maybe not. So we cut it again, and again, and up to the time where we're happy with it, right? So it will depend, right? And basically, the claim is that there is one. And when you have this partition, then what you do is you take the mean value, the vorticity, on each of those domains. I should have put here, explain this is time. So this, because we integrate in Tx, and this is x, but this is the boundary, right? So this is x1, x2. So my picture is x1, x2, and if you are 2D, which is good to think 2, it's really then 2D because the boundary is 1D, the time is 1D. So it's 2D, but it's time space, okay? And you take the mean value here. And basically what we can is that almost, well, it's not exactly this, but I do it, we have the L3 over, is almost, because it's not the L3 over 2, right? It is what you get by Chebyshev, but it's almost saying the L3 over 2 is controlled by the gradient 2 L2. But of course, it's for any solution of Navier-Stokes, so it does not depend on the domain, right? So you can say, well, let's do it for very large time, very large domain, and then you can rescale back and say, well, actually, this was a solution. The solution that I wanted is to have on a solution of with nu very small. So I do, you can see there is no nu in front here, or 1 over nu, because is I take a solution with small nu, I rescale like this, and I get a solution of Navier-Stokes with nu equal 1 on a very big domain. I apply my inequality here, I replace it, and I obtain exactly this inequality. And that's why I say it's rescalable. And it means that I control exactly what I want, the new omega, right, through my dissipation. That's how I say it is rescalable. Right? Why the omega theta is still fine? Why? Because if I go back to this computation, when I spent a bit of time there, of course, I want to integrate in time, right? So this means that this quantity I want to integrate in time and position, right? And if I integrate in time and position, if I took some mean value, it doesn't change the integral, right? So if I took the mean value in terms of in some domain, well, since I integrate everything, the mean value or not is the same. And that's why I don't have problem with that. And now I will finish. I mean, I finish is just by saying, well, I do is this is L3 over 2 times L3 of A, and is a little bit of the L3 over 2, which can be controlled by the dissipation, plus a large bit of the L3 of A cube. And this is A cube, right? Which is L3 of the constant A times the size of the box omega, which is 1 times T. And that's how we get the estimate, right? Is that simple, right? So what is behind is really having a control on the vorticity, it is a regulation effect. So you have to do it as nu equal 1, but do it in a way that you have that is scalable. And in some ways, the fact that you find something scalable seems a bit too much, but in some way we knew possible because in other contexts that's what we are doing, and this line of work of a contraction theory for stability of 1Ds is something that I'm working a lot with Moon-Jin Kong. And especially this example working for Navier-Stokes, having an estimate which is uniform with respect to the zoom was for shock, and is really in the of dimensionness of this paper. Right? Of course, the proof will be very different and it will be very incompressible, right? But in the spirit, this comes from here. I should say another thing here, the fact that we have a boundary is very important. Here we didn't have boundaries, so the context is actually more complicated, except it's 1D, right? So there's a balance of difficulties, right? We are 1D, so we can work far away from boundaries. Here for the result that I showed today, I don't know, actually work with it. Okay, so I would like to give an idea why it can be true. First, it's not at all about the proof, but why, I mean, where this estimate comes from, right? I mean, in terms of ideas. Well, okay, so we consider Navier-Stokes, as I say, is Navier-Stokes nu equal 1, right? This is a dissipation term, gradient UL2. And just for fun here, I mean, by this I mean, the proof won't be like that, but I consider the vorticity equation. So you consider the vorticity equation here. And again, we will say, okay, let's assume that the transport equation is not the problem. Well, actually, sorry, the transport equation is this, right? Let's assume that the transport equation is not the problem. And it's true that most of the time, right, it's not the problem, right? I mean, the worst part does not come from here. So let's forget about that, and let's try to do just elliptic parabolic regularity, right? And I say, okay, well, this is L1, this is D, right? This is omega time gradient U, so it's L1. Okay, it equation not good for L1, but it's limit case, right? And anyway, we have a problem, which by the way is slightly linked to this. So, well, we have almost two derivatives of the vorticity, which is controlled by L1, okay? And you can say, okay, so let's look, then do a bit of interpolation, trust me that, because I know that it's L02 that I want at the end. So I just do here is two derivative, omega is one derivative, I do some interpolation, I get this respect to D, and then I do the trace, because I have 2/3 of derivative, and I have this and exactly what I get. Right? This is my estimate. This is a vorticity on the boundary at L3/2 at the power 3/2 bounded by the dissipation. Why I'm very happy with this? Because again, you trust me or you do the computation. This is you can rescale this quantity through the inviscid limit. Right? That's in some ways this is where the thing why this is important. Okay, so you could say, wow, then it's that easy. Well, not that fast, because actually, for this kind of problem, the transport term is the worst. The transport term is very bad, and you can look at here. If you try to control U gradient U, we would need U gradient omega to be in L1, and if you look at the best estimates that we have, well, I do it symmetric in TX, so you can play with the things. So it's easy. Well, for dimension 3. You cannot even control this in L1, right? So U gradient omega, you don't have enough estimate. You have in TX 10/3 for U, and for gradient omega, I mean, this is using the business of a higher regularity. If you heard about that, it's something I was involved in sometimes. The best you can get, and now we are pretty happy because we, even with the same Jincheng Yang, we're able to improve this, but you still have L4/3, 4/3, 10/3 does not work, right? I mean, you 4/3, you need L4, 10/3 is less than 4, okay? So this means that they are not in duality. Even with the best technical that you can hope, U gradient omega is not controlled, which means that everything, the difficulty is into the transport part, right? And well, the idea that we do is that actually we had exactly the same kind of problem before, and that's what we were trying to get a higher control and higher derivative for Navier-Stokes. And when you do this, you get exactly the same problem. The problem is a transport, and we developed at the time. I say we, I begin, and then there was student Choi, reminds the time, and we find a way which was involving blow up, and in some way the idea was using some explicit control from the blow up techniques for partial regularity. So in some way, partial regularity, you can say, well, what you get is implicit result, right? I mean, size of domain where, I mean, size of domain where things are bad, right? I mean, again, there's a lot of expert here, but then you can say, well, let's try through the zoom to actually explicit what you get, right? And that's basically, and get it in some LP. And basically the idea is to do this where we were using it in order to have norm for higher derivative. We say it's not higher derivative that we want, it's trace. So it's the same idea. And the fact that the higher derivative works a bit like trace is kind of natural. I mean, you know, I mean, the trace, what we call trace theorem, is to say if you have higher derivative, you can get a value at the boundary, right? So we don't go through the control of higher derivatives, but in terms of spirit, it's very similar. So it relies on what? Well, again, if you're familiar with this, always the partial regularity result, it involves some law. And the first one is to say, well, if you control on locally the gradient, the dissipation, right, on the ball of order 1 after zooming, right, if you have something, you control it, then you can say locally, then you have something smoother, right? So it's saying that, so now it won't be on any point inside, you do this on the boundary, you say that locally above the boundary, if you control the viscosity, then you control the regularity inside. Right? And then when you have that, well, you play with the scaling of now is Navier-Stokes equation, right? So it's the epsilon, because it's now a regularity result at the level of Navier-Stokes, right? So nu equal 1. So it's basically those two ingredients, right, that we use. There is some difficulty. There is some difficulty because of the boundary. When I say that things are nice with the boundary, not everything. There is some problem here. And basically, and one problem is that you want to control everything just using the gradient U without looking at the vorticity, the pressure, right? I mean, this is the main thing. And you know that most of the result of this kind, partial regularity, you need some knowledge on the pressure. Actually, not all this recent result when you can get rid of a bit of them. But that's the main thing. We do not control the pressure on the boundary, even at the Stokes level, is very bad. If you don't have a global control, you are in a bad situation. And that's where the mean comes from. We cannot control the vorticity. I think it's not possible, actually, in the context we do, the vorticity on the boundary just by control gradient U, right? And at the Stokes level, it's not possible. You can look at some counterexample because of oscillation in time, right, of the pressure, right? And basically what we do is we smooth out the oscillation in time by smoothing the vorticity at the level, and this level where the gradient U is under control, right? And that's why those mean are important, right, in what we do. Okay. Maybe I can show a bit more how things work with a couple of pictures. So this is our situation, right? So again, if you want 2D, just to simplify the idea, this is 1D, this is the boundary, this is time, right? So this is the map. You want to have an estimate on the mean value of the vorticity, integrating X and time, right? So that's what you want. Okay, so you know, so basically how we do the cutting here, well, we cut in order to be able to say that locally the gradient U controlled, right? Because this is a local thing, but it's local on the boundary. So for this, you need enough time because this is a regulation effect, right? I mean, so that's why you need to cut pretty thinly when t is equal to 0, right? Because you're having time. And then you integrate. While you integrate, so let's say it would be what? Of course, here you have just your boundary, right? And your gradient U lives above. So actually what you consider here is for each of those quantity, what you do, and in the third dimension is going inside the domain, right? Because you have boundary, time, so inside of your tunnel, right, is going to my face here, inside the tunnel, right? So, and this is a third dimension, and now you have here something which is a cube integrating in all things, right? And this is this cube above your boundary, and this is where you measure the integral of gradient U squared dx dt. Actually, not exactly up to maximal function, because you want to measure a bit elsewhere. Well, is also techniques. Maximal function is something that behaves like gradient U squared, but taking a bit of information outside of the ball. Okay, so that's also something pretty standard here, right? And basically, what you do, you say, well, if this is smaller than eta, then I don't chop it anymore, right? Because I will, well, it's not eta, it's after rescaling, because you want to, then you rescale, right, to have order one, and after rescaling is of order one, so this means that actually this thing, you rescale in order to have a ball, now, I mean a ball, a cube or whatever. And here it's over the one, right? So after rescaling through your scaling of Navier-Stokes, the Navier-Stokes, right? And that's why you have this kind of rescaling here, right? If you rescale it and you say, well, here it's smaller than eta, right? Then you say, oh, but then on the boundary here, on the boundary, my vorticity is controlled. Well, after smoothing, because obviously you will use some regularity, non-linear and then linear, so you will need Stokes. Stokes says that you cannot get more regularity because there's counterexample of association in time. But when you're regularized in time, then you're fine. You get this regularity, right? So this means that, okay, so here you will have exactly control of omega. But if it's too big, well, if it's too big, then you chop it, right? And you chop it. And then you measure again above. Maybe I won't do another picture, well, just once. Okay, so you measure again the energy that you have above. If it's too big, then you chop it again, and you chop it again to the time where everything, all those energy above, all those cubes are of order that after scaling, they have order one, right? And so this means that on all those one, you know exactly the omega tilde, you control it, but you control it exactly with respect to your scaling, right? So you can compute the scaling. And then what you do is, of course, you will want to integrate on each cube and sum them all up. So you need that on each cube, the integral is the same order that you know, which is the gradient U squared, right? Which is of order exactly the eta, right? And when you look at the scaling, well, this would give you 302. So basically, you get this, you put everything, and you solve any integrating them up, right? And by integrating them up, you get that this omega is controlled, the vorticity on the boundary is controlled by the dissipation itself. What more I should say? So, I mean, we are pretty happy with this. We first gave an answer result up to a log, right? But then you see, I mean, on all those things, especially when you go up, what we measure is not really integral. What we measure is, well, the size of the set, right? And that's why at the end we have, but we were able to get to the limit case. Whether we can get an integral things is not clear, right? And it's really linked to difficulties that we had already working with higher derivatives. The first result was exactly the same kind. It was with a weak, L infinity weak. The new result that we have with new technology introduced with, I mean, with Jin Cheng, but that was really put in place by Jin Cheng, we were able to put, well, almost, we have not the 4/3, right? But at least we have integral and pretty high integrability, I mean, up to the limit case, not the limit case, but up to the limit case, right? As a limit. So can we do it? It's not clear. The next work would be to do it not on the boundary, but in the domain, which would be even more interesting, I think, right? This would be, if you have a shear flow inside a domain, can you also control the size of the possible separation here? I mean, in physics, you really see it, right? I mean, you cannot have a clear flow. I mean, you always have a separation, right? And actually, they measure it. And if you look at some physical papers, they give exactly the CAQT, right? So it has to be that, right? It has to be that. Why it's complicated? Actually, this computation of trace will be, I almost simple, will be different, let's say. But here, I think that we won't need the mean value of the vorticity because the regularity inside is better than on the boundary with the pressure, right? So things are better with the pressure inside than on the boundary. The problem is that here, everything, we look at the boundary, we stay on the boundary, right? So bad things stay on the boundary. While if you, the first thing which happens is a transport at the level of, means that you have at the level of incompressible things which move, and this you have to control them. And usually you control them with another way. We know how to do this for compressible, but it seems to be hard to put it in the incompressible world, right? So that's where we are. It's controlling not at the level of Navier-Stokes, not the diffuse term, but at the level of Euler. Again, it's because when you're on the boundary, right? Yeah, this is this computation, right? When you're on the boundary, all the Euler term vanish, right? You just have the term of the viscosity. This is not true when you're on the inside. Things are more complex. And I think it's time to stop because otherwise I will never stop. Thank you.
Okay, well, that's thank you, Alexis, very much. All very impressive.
Thank you.
So, would people like to unmute and ask questions?
I have a couple of questions, if that's okay. Maybe the first one, maybe a silly question. So you said in the beginning that you're a priori bound to have the constant C that's universal, while Sekihide Jr. has shown that for any constant, no matter how large, you can get wild solutions.
So
right?
yeah, for Sekihide, no, for Sekihide, any constant smaller than 2. So there is a number associated.
Less than 2.
So,
I see. Okay.
Yeah, I don't know where am I.
Okay, that's okay. You probably missed that.
Yes, theorem here. Yeah, is C smaller than 2.
Okay, that makes sense.
So yeah, so there is a limit here. For Sekihide, it's based on it's convex integration. So it's the L infinity, what they call sometimes the L infinity theory or the old theory, which is based on finding a subsolution and then you convex integrate. So basically, all the stress there is on finding a subsolution, and the subsolution is constructed. I mean, the degraded is just constructing solution for a certain Burger's equation at the end, right? And for this Burger's equation, well, it's explicit, right? So things are explicit, and this is explicit, and they find C is smaller. It doesn't mean that you cannot convex integrate with a bigger C, right? It just means for convex integration for this specific kind of subsolution, their limit is at 2. And for us, the constant come from the constants on the regularity at the Navier-Stokes level, right? And these constants, it's pretty hard to track. Yeah. So it's really there exists one.
I have some more questions. So Secondly, you mentioned later that when you obtain your estimate on the vorticity, you have a problem with the transporter U times nabla omega. So I wonder, like, sometimes you can get rid of these kind of problems by looking at Lagrange coordinates. You kill the transporter. I wonder if there's any chance that you would look in this direction and get something.
Well, that's a very good point. Actually, I would claim that in some way, this is how this is the idea behind those techniques. This is the idea behind these techniques, because those techniques was already because the transport was bad. So what we were doing here, again, here the fact that we're on the boundary, things are slightly easier, right? But we will, if you do it in the inside, then you will need this. And but just to rely on what you were saying is, well, actually we do not in those contexts, which are very, very small, very, very, very close, we do not go. I'm cheating when I say that this is equation that we're, the scaling that we're doing, right? It's not the scaling that we are doing. The doing is this up to a shift.
Mm-hmm. Mm-hmm.
And what is this shift? This shift is flowing the flow of you. So it's almost, you know, I mean, it's almost a Lagrange, but doing the flow when you regularize it at epsilon. And when we do this, is because you want Lagrange, as you say, in order to kill as much as possible of the transport term, but you want to stay Euler because you want to see the regularization effect, right? And that's what we're doing here. We say, okay, we are trying to kill. So we take, in some way, you take those molecules at epsilon level here, and we say, well, this is where the diffusion take effect. So I want to see the diffusion effect. But usually it does not work. Why? Because if you just zoom here, if you have a big drift, a big mean value here, what's happening is that your flow is just flowing past all the time, and you have no time to regularize. So then they say, well, then you take the mean value, solve this. Well, actually, it's x dot or u of x plus x, right? I mean, it's non-linear, right? So you're following this flow, right? And now in the window where you're looking at, right, you don't have this huge drift. You still have the non-linear term of your transport, but not the huge drift, right? And that's what's already what was needed here in order to higher regularity, right? And this is in the same spirit that we're doing here, right? It's the same spirit. So of course, the fact that you know that you exactly go to the boundary help a bit, right? Because you know that you don't really need to have, but in some ways for the same reasons, you know, you don't have those weird things that go past and you don't have regularity, right? Mm-hmm. This is the thing that you don't think when you regularity, because you know, well, I mean, okay, but if you want to do, because the techniques are very partial regularity, right? It's really you zoom and you say when it's small you have something. But now if you want to say why you don't need it, because for when you do partial regularity, you take a sequence and you say, well, maybe it goes too fast. Well, it's another way to see what you're doing. Is to say, well, why we do this sequence? Because maybe we're going too fast, there's no regularity. So we zoom in and we say, well, now it's not too fast. I zoom in again. Maybe it's not too fast. And you know that at one point it won't to be too fast, and then we'll go after the regularization. I say I cannot afford that because I want to, you know, to compute right away and saying when I epsilon what I have. So in order not to do that, I follow the flow. And what is, and just since you give me the things, how we manage to improve here, and I think it would be useful for all the things, right? So those techniques get L infinity, L whatever, LP weak, right? And this is again LP weak, the result that we have here. The way to increase this was because through those transports, things were good, but not for the maximal function. Maximal function does not, okay, the maximal function, right? You remember I said it's not gradient u, it's maximal function of gradient u that we want. When you distort things, it's not good for the maximal to distort things like this. And that, and actually, well, I had the idea to this, but really it was put in place by Jin Cheng. It's a paper just by himself, because I was really impressed how he put this. He was able to, he defined a family of maximal function, which are not with respect to a fixed ball, but with distorted ball with respect to the flow. So it's really, it's very close to what you say. You want to do to Lagrange, but not completely, because you want still to see the ball. So you do this, but there is bad things which happen, and this is where we're trying to push techniques, right? I mean, I'm just saying this because it's a very nice new introduction of Jin Cheng, or also in this context, is to say, well, you have to bring more things because you work between Lagrange and Euler, and especially this Maxwell function is really very nice. I mean, this is a short paper. It's very nice. Yeah.
I see. Well, in fact, I kind of see, because I was reading your paper from 2010 before, and in fact, the control of the mean was the key there. As far as I could see, is that for this kind of a priori bound solutions, you really needed the one scale partial regularity, but also scale optimal. And the only way you could do it, as far as I could see, was to control the mean. Once you control the mean, you're done, right?
Exactly.
And
exactly. Yeah. So you want to get the mean out, right? I mean, it's really this picture, because if you have a huge drift, well, the regulation is to say you are in a ball, you fix everything in the ball, you have the viscosity which does its job, it's regularized. But if you have a drift which always bring you in your things new material, it doesn't have time to regularize, right? So what you do is you follow. Yeah.
If I may ask about the maximal function, that's my last question. So at the end, you mentioned you take the maximal function of a gradient u squared.
Yes.
And I wonder how does that work? Because you have the maximal function is not L1 bounded, right? And the gradient of u squared is just integrable, right? So is there no problem there?
No, but you're right. This is a limit case which are really terrible, right? So especially here, this is I'm sorry I'm talking about something else, but this work, in order to get that, here you're completely right. Completely right. And one of the difficulty was to work not on gradient u squared, but maximal of gradient u to a power strictly smaller than 1, right? Which is weird, because you control Navier-Stokes with a quantity which is less than quadratic. Right? So that's something deep there. There's something deep there. But here we don't need it because we just want L1 weak at the end. So what we use is that the maximum one is L1 weak.
I see. So
that's the maximum, because you have to go from L1 to L1. But we're stuck in L1 weak, right? But that's why we don't need it here, right? But you're completely right for the other things, right? And that was another very subtlety.
All right, thank you.
So, are there other questions? Any further questions?
Is it possible for some like other stationary solutions? Is it using very essentially it's a shear float approach?
Yeah, that's a good point. Is how it depends on what we on the decision that we have. So we first went for the simplest, right? Obviously, now so Jin Cheng is actually working on trying to see how to extend that, and I think that it's very important because even for physics. So let me, and then I will say what we know. We don't know much yet. But when I talk about this situation, I try to warn you to say, well, okay, it's not exactly what we're talking about, because here we know that the bad things happen also with respect to the angle of attack here, which means that it may depend on the pressure, right? Because it means that you change the pressure. We know the pressure positive, negative, for the solution, I mean, layer, the Prandtl layer. This is very important too, right? Does it depend on the Prandtl layer when it's stable, unstable? All those are very important questions. And so I think it's really important, it's not only again how far we can go. And I think that my gut feeling is that it should go for most of the situation actually. I think that the situation of what I was just saying, right, is for the next level, but at the level of size of the layer separation, this shouldn't depend. So what seems clear is the boundary, the size, as long as the boundary is smooth, the fact that it's curved shouldn't change, because basically what we want, I mean, what we want is a Navier-Stokes equation, I mean, the result as Navier-Stokes level, and we just need to have it uniform with respect to the boundary. But anyway, we'll use it by zooming, right? So we just need to say, well, if you zoom something, well, we just make it smoother and smoother, right? So that should go the right way with respect to scaling. The question which was completely clear the last time I talked with Jin Chang, if the U depend on time, if you have the Euler which depend on time. I mean, you have to be careful, right? Because you have to smooth the vorticity, so there are things non-trivial happening here. I'm still hoping that that shouldn't change much, but we have to be careful.
Yeah, and the second question is the result is consistent with the solutions converging to one of these Euclidean solutions, right?
Exactly.
That's what this is saying. Yeah.
Okay. Yeah, exactly. It's and you have the right word, consistent.
Yeah. Yeah.
Yeah. We don't know.
Thank you.